Today I'll cover how to predict SN1, SN2, E1 and E2 reactions. So before we start, I want to recap the highlights from my previous video about mechanisms of SN1, SN2, E1 and E2 reactions. So one thing you have to remember is for E2 reaction, you need to have an anti-periplanar beta proton. And the beta proton is on the adjacent carbon. And the product that's formed from E1, elimination reaction E1 or E2, is an alkene that has the carbon-carbon double bond. The next thing to remember is both E1 and SN1 mechanisms will result in a carbocation intermediate. The product that's obtained from an SN2 reaction will have an inverted configuration. So if you start with a chiral center, you will end up with a chiral center in an SN2 reaction, but the chiral center will have an inverted configuration. You can learn more about the R and S nomenclature for chiral center in my videos. For SN1 reaction, since a carbocation is involved, that will result in a racemic product because the nucleophile can attack from the front side or back side of the carbocation. And always remember that substitution and elimination reactions will occur only at sp3 carbon. They will not occur at a sp or sp2 carbon. So in the next few minutes, we'll learn what factors control the different types of substitution and elimination reactions. So there are three main factors. One is the substrate that will control the type of reaction. And then you have the nucleophile or the base. The next factor is the solvent. The solvent will also play a role in deciding which product will be the major product. We will go through each one of the factors to better understand how to predict the type of product and the type of mechanism. So let's start with the substrate, nucleophile, and the base. So there are different types of substrates, and that's based on the branching. So primary substrates will have a straight chain, and then you can also have a primary branched. Branched means it's going to be branched at the beta carbon that's next to the primary carbon. And then you have the secondary substrates and tertiary substrates. Please refer to my video on naming alkanes that explains more about primary, secondary, and tertiary carbons. And then you have two different types of nucleophiles, poor nucleophile and moderate and good nucleophile. And in these two columns, you have the base. The base can be an unhindered base or it can be a hindered base. So if it's a strong hindered base, you will always get a E2 product and the reaction will proceed by E2 mechanism. For an unhindered base, you'll get E2 product, except in the case of a straight chain primary haloalkane. So what's an unhindered base? Well, you have hydroxide, alkoxide, dimethylamide. These are all unhindered bases. Hindered bases example is T-butoxide. This is tertiary butoxide, and this is diisopropyl amide, anion. So if you see this hindered base, that means the reaction will always proceed to E2. Whenever you see a base, it's going to proceed to E2 with the exception of primary straight chain haloalkanes. And this is typically true for any other living group. In this haloalkanes, the halo group is the living group. For nucleophiles, it gets a little bit tricky. So poor nucleophiles do not react with primary haloalkanes. Secondary haloalkanes will give SN1 or E1 because they proceed through carbocation. So we'll see that nucleophiles will favor SN1 and E1 for secondary and tertiary substrates, and that's because of steric hindrance and the carbocation stability. To learn more about the carbocation stability, please refer to my previous video on carbocations. It will explain why tertiary carbocation is more stable than secondary, which is more stable than primary. Another point to remember about elimination reaction is that elimination reaction will not occur if the beta carbon atom does not have any hydrogens on it. So in case of tertiary haloalkanes, the E1 elimination will occur, and it can be a haloalkane or alkyl sulfonate, but the solvent needs to be non-nucleophilic. For moderate and good nucleophiles, the primary haloalkane will result in an SN2 product, whereas for a secondary, depending upon the conditions, you can have SN1 or SN2. Whereas for tertiary, it will always proceed via SN1 or E1. And we'll cover examples under which conditions you'll get SN1 and E1. So here there are some superscripts here. The pound sign indicates that this will happen only for very hindered haloalkanes or alkyl sulfonates. And because of steric hindrance, the nucleophile cannot attack the center directly, so it has to go through a carbocation for secondary. So, as you are aware, loose bases are nucleophiles and they can donate a pair of electrons. These are the different examples of loose bases. You have alcohol, thiol, amines, phosphine. X is a halide group. R, this is alkoxide. R is an alkyl group. And you have all these different anions. You also have ammonia right here. This is azide. So you have neutral molecules as well as anions that can donate a pair of electrons and hence can act as nucleophiles. So the nucleophilicity will increase as negative charge increases. So a neutral molecule is always going to be less nucleophilic than an anion. As you move from top to bottom of the periodic table within a group, then the nucleophilicity will keep increasing. The reason is the atom size increases, so the electrons are far away from the nucleus, and hence iodide will be more nucleophilic than fluoride. But the nucleophilicity will increase if you move from right to left within a period. In case of ammonia and water, that's a very good example. Both ammonia and water have lone pair of electrons. But if you consider the size and the electronegativity of the two atoms, you are aware that oxygen is more electronegative than nitrogen. And hence it will manage electrons much more strongly than nitrogen. And for that reason, ammonia is more nucleophilic than water. So let's list some poor nucleophiles. Water, hydrogen sulfide, alcohols, and carboxylic acids are all poor nucleophiles. These are all neutral molecules. Moderate and good nucleophile examples are phosphines, ammonia, amines, thiols, phenoxide. pH is the benzene ring. You have the carboxylate anion and the azide and cyanide. These are all moderate to good nucleophiles. So let's look at the third factor, which is the solvent. So there are three types of solvent that are typically used in organic reactions. The first one is the polar protic solvent. Example is water, methanol, ethanol. Protic because the solvents have a hydrogen that's either attached to oxygen or nitrogen, and it can help in hydrogen bonding and stabilizing the carbocations, and it also can act as a nucleophile. The other type of solvent is the polar aprotic solvent. So in this case, there is no OH or NH. So aprotic solvents cannot do any hydrogen bonding, but they are polar. Example is nitromethane, acetonitrile, DMSO, hexamethyl phosphoramide. And the last class of solvent is a nonpolar solvent. Example is diethyl ether, toluene, and tetrahydrofuran. So nonpolar solvents don't stabilize the carbocation, and so they will not favor an SN1 or a E1 reaction. So a couple things to remember, that polar protic solvents will favor SN1, whereas aprotic solvents will favor SN2. If there are two leaving groups in the molecule, then the atom that can best handle the negative charge will leave. And how do you decide which atom or a group is going to best handle the negative charge? You have to see if the anion can have resonance, or if the size of atom is large. So larger the size of the atom, better it can handle the negative charge. So in protic solvent, nucleophilicity will decrease as we move from left to right, as is the case as we move from carbon to fluorine, or from phosphorus to chlorine. And also nucleophilicity increases as we move from top to bottom. Most important thing to remember is the nucleophilicity trend reverses in a aprotic solvent. So whenever you see a aprotic solvent, just pause and remember this rule. Let's talk about special cases. Alcohols are unique in their reaction with hydrogen halides. So if you have a primary alcohol, it will react with HX, that's a hydrogen halide, via an SN2 mechanism. However, if the alcohol is secondary or tertiary, then it will react via SN1 mechanism. In both cases, the first step of the mechanism is protonation of the alcohol, which it will then lose a molecule of water to give the carbocation if the reaction proceeds by an SN1, or the protonated water can act as a leaving group with a concerted attack by the nucleophile on the reaction center via an SN2 mechanism. If sulfuric acid is present, then it will dehydrate the alcohol to form an alkene via an E1 reaction. If you have cycloalkanes, then it's a unique situation. An E2 reaction will occur if there's a beta hydrogen. Otherwise, E2 reaction will not occur. And the beta hydrogen needs to be anti to the leaving group, or anti means opposite direction, and we'll look at an example. Let's consider this secondary alcohol. In HCl and water, the first step is protonation of the OH group by HCl, and then H2O is a good leaving group, so that will result in a secondary carbocation. The secondary carbocation will see two nucleophiles. One is the chloride and the other is water molecule. If you recall that an anion is a better nucleophile than a neutral molecule, and so the chloride ion is going to attack the carbocation from the front side or the back, because the carbocation is planar, if you recall, and you'll get a racemic mixture. So the reaction proceeds by an SN1 mechanism. Let's look at another example. In this case, I've made a model to help you understand. So let's look at carbon atoms 1, 2, and 3. These are of interest. And the reason they are of interest is chloride and iodide are the living groups. And this is the hydrogen right here that can be abstracted. Sodium ethoxide is a strong ionic unhindered base. And this is a protic solvent. So if you recall, an unhindered base is going to abstract the proton. And this is a secondary alkyl halide. So it will proceed via a E2 mechanism. So in order for the E2 mechanism to occur, you need to have a beta proton. The only beta proton that's available is this hydrogen. Beta protons are the protons which are next to the carbon bearing the living group. So in this case, the carbon bearing the living group is carbon 1 and carbon 3. And so the beta proton is on carbon 2. There is no beta proton on carbon 6 or carbon 4. Okay. If you recall that among the two living groups, chloride and iodide, iodide is a better living group because it can better handle the negative charge as compared to chlorine, because iodine has a larger atom size as compared to chlorine. However, as you can see from the product, that the chloride is lost and iodide stays. And the reason for this is because this hydrogen is anti or in opposite direction of the living group. And for an E2 reaction to occur, if you recall, the hydrogen, the beta hydrogen, needs to be anti-periplanar to the living group. Whereas in case of iodine, this hydrogen is on the same side, so it's not anti. So let's look at the model. So this is the model I created, and you can kind of make your model, and by the set, I think it's very useful. This one is the iodide. I've just kind of just for color coding purposes, it's easier to look. This is iodide, and this is the hydrogen on the carbon atom, and you have, this is the ethyl group, and this is the beta. This is the beta carbon with the beta hydrogen right here, and then you have the chloride. This is the chloride. Okay, so you can see from this model is the chloride. This is right here. This is the chloride is anti or in opposite direction of the beta proton. This is the beta proton. Okay. Whereas in case of iodide, this is iodide, the beta proton is on the same side. And so, although iodide is a better leaving group, the E2 elimination will not occur with iodide because iodide and the beta hydrogen are on the same side. So I think it's useful to make the model to better understand why the stereochemistry and the locations and the positions of the beta hydrogens with respect to leaving group. So let's look at another example. In this case, this is a primary alcohol, and the reaction is occurring in ether as a solvent, and hydrochloric acid is used. So the first step is protonation of the alcohol, but after protonation, the H2O will not leave because primary carbocations are not very stable. Please refer to my video regarding stability of carbocations to better understand why primary carbocations are not formed. Because primary carbocations are not formed easily or readily, therefore the chloride will then attack this carbon center after the hydroxy group is protonated, and you'll get alkyl chloride via an SN2 mechanism. Let's look at another example. In this case, sulfuric acid is used, and you have the alcohol. It's a secondary alcohol, so the first step is protonation of the alcohol, and because it's secondary alcohol, the protonated alcohol will lose the water molecule to form a carbocation, and the carbocation will then lose a proton, a beta proton, via an E1 mechanism to give you the double bond or alkene. Important point to remember is HSO4 anion or phosphate anions are not nucleophiles because the negative charge is delocalized on several oxygen atoms, and whenever you have the negative charge getting delocalized on several oxygen atoms, then it cannot act as a nucleophile. And so the reaction proceeds via E1 mechanism and elimination occurs rather than a substitution. So let's look at more examples. So this is a secondary alkyl halide. The reaction is occurring in nitromethane as a solvent, so it is a polar aprotic solvent. The base is, it's a weak base here, triethylamine, and so the way the reaction will occur, because it's a secondary alkyl halide, it will prefer to form the carbocation because there is no nucleophile. Triethylamine does not act as a nucleophile. And so once the carbocation is formed, then triethylamine will abstract a beta proton. So it can be this beta proton or this. But if it does abstract this one, this beta proton, then you'll get the monosubstituted alkene that's not favored. If it abstracts this beta proton, then you'll get a tri-substituted alkene, and that's favored. So always remember that a base will abstract a beta proton that will result in the most substituted alkene. So this is a tri-substituted alkene. If you want to learn more about the different substituted alkenes, please refer to my video on alkenes or classification of isomers to learn more. So let's look at another example. In this case, this is again a secondary halide, and secondary halides in presence of methanol, and this is sodium hydrogen sulfate. So this is an anion, but this is not a nucleophile. The reason it's not a nucleophile is because the negative charge on oxygen is distributed between 4 oxygens, and therefore it doesn't behave like a nucleophile. So the nucleophile in this case will be methanol. And methanol is going to attack the carbocation, which is achiral, and that will result in a racemic product. So let's look at another example. If you look at this example right here, remember that you cannot have a nucleophilic substitution or elimination reaction at sp or sp2 carbon atoms. So this is an sp2 carbon, and so no reaction will occur, although this is a good nucleophile. Let's look at another example. This is a strong hindered base, so it prefers an E2 elimination reaction, but you can see, look at the substrate, there are no beta hydrogens here. There are no beta hydrogens, and because of that, there won't be any reaction. Let's look at this example. This is a tertiary halide, and T-butanol is a very weak nucleophile or poor nucleophile, and so this tertiary carbon or halide will lose the chloride and form a carbocation. The carbocation is stabilized because it's next to the phenyl, as well as it's next to 2 methyl groups, and it's a tertiary carbocation, so it's much more stable, and so it will be formed, and then T-butanol will attack the carbocation from either side. So let's look at another example. This is again a tertiary halide, and in presence of triisopropylamine, and THF is a solvent. THF is a non-polar solvent, and so a carbocation is formed, and then triisopropylamine is going to abstract a proton to give you the alkene. So let's look at additional examples. So in this case, you have a primary halide. The base is sodium methoxide. It's an anion, and the reaction solvent is methanol. So sodium methoxide is a better nucleophile than methanol. It's a strong unhindered base, and since it's primary, if you recall, it can attack the carbon center via an SN2 mechanism to give you the ether. So let's look at another example. In this particular case, this is a secondary halide, and there's a double bond next to it. The reaction occurs in ether. Ether is a nonpolar solvent, and hydrogen sulfide is the nucleophile. So in this case, the reaction will occur by an SN1 mechanism, and the product will be racemic. So let's try to rank the substrates in order of the rate of SN1 reaction with ethanol. So these are the different substrates, and take a look at that and write down the answers, and once you have the answers you can check it. So you can see that this is a sp carbon. Nucleophilic substitution or elimination reaction will not occur at an sp2. Therefore, this is the worst substrate for a SN1 reaction. SN1 reaction involves carbocations, and so primary, as you are aware, primary halides cannot give the primary carbocations because primary carbocations are not very stable, and hence this particular primary halide is ranked number 4. Then let's look at this tertiary halide. So for a SN1 reaction to occur, tertiary halides are pretty good because a carbocation can be formed, and however, if you have a double bond or a phenyl group next to a carbocation, it's much better stabilized than a tertiary carbon. And so this tertiary halide is number 3. In case of this one, you have a double bond, and so the carbocation will go into resonance, and it's much more stable, and so it is ranked number 2. Whereas the best one is one which has the phenyl group attached to the carbocation, because the carbocation positive charge can get delocalized in the phenyl group or the benzene ring, as well as in the double bond right here. So you have to look at the resonance structures to see which carbocation is the most stable. Whichever is the most stable, that's where the reaction will occur fastest via SN1 mechanism. Let's look at another example. This is a secondary halide, and this is sodium acetate. Acetate is a moderate nucleophile, and the reaction is occurring in DMF to help speed up the reaction. DMF is aprotic polar solvent. So aprotic polar solvent will make the acetate a better nucleophile. And so the reaction will occur via an SN2 mechanism. Let's look at this alkyl sulfonate. In presence of sodium methoxide in ethanol, it will proceed via E2 mechanism. Sodium methoxide is going to abstract a beta hydrogen, and this, since it's a primary, it will not form the carbocation. It will prefer to undergo E2 elimination. So let's look at more examples. So this is a primary alkyl iodide, and you have a solvent which is dichloromethane, and 2 nucleophiles, chloride and bromide. Remember that in a aprotic polar solvent, the nucleophilicity trend of halides is reversed, and because of that, chloride is now a better nucleophile, and it will replace the iodide via an SN2 reaction. The substitution reaction occurs because it's primary, and primary carbons cannot form, they can form carbocations, but they're not very stable, so that's not the preference. Let's look at another example. In this particular case, you have 2 leaving groups, iodide and chloride, and you have 2 nucleophiles, ethoxide and ethane thiolate. And the reaction is being run in a polar protic solvent. So between the 2 leaving groups, iodide is a better leaving group because it can manage the negative charge better. And between the 2 nucleophiles, ethane thiolate is a better nucleophile as compared to sodium ethoxide, because it can donate its electron pair much more easily. So that's the reason the reaction proceeds via SN2 reaction mechanism, and you get the substitution product. Let's look at some examples and try to rank order the nucleophiles which are listed right here for a SN2 reaction with propyl bromide. Remember that propyl bromide is a primary alkyl halide. So after you have written down the answers, you can check it, and this is the correct answers. So always remember that neutral molecules are the worst. In this case, bromine is the worst. Phosphine is better than bromine is because it has a lone pair of electrons on phosphorus, and so it can donate those lone pair of electrons and act like a nucleophile. In case of fluorine, OH, NH2 and CH3, you can see that if you look at the periodic table, you are moving from the right to the left in the periodic table, and as you move from right to the left, the nucleophilicity increases. And so CH3 anion is the best nucleophile because it can donate its electrons much more easily than fluoride. Fluoride is most electronegative element, and so it will hang on to the electrons much more tightly as compared to carbon. So let's look at another example. In this particular case, you have 2 living groups, chloride and cyanide, and you have sodium phenoxide. pH is the benzene ring. The negative charge on oxygen is right here. It's not visible, but it's there, and the reaction is occurring in TMSO to enhance the nucleophilicity of the phenoxide anion. So the reaction proceeds via an SN2 mechanism, and chloride is displaced in preference to cyanide because chloride can handle the negative charge much better than carbon. So let's look at the last example. This is a secondary alkyl iodide, and you're heating it in sulfuric acid. Heat favors an elimination reaction. So in this case, since this is a secondary alkyl halide, it will give rise to the secondary carbocation, and the carbocation will then undergo elimination to give you the alkene. Thanks for watching. Like and subscribe.